Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and today we're diving into a technology that could redefine how we power everything, from smartphones to electric cars: solid-state batteries. If you've ever charged a phone, driven an EV, or worried about your laptop overheating, you've experienced the limitations of current lithium-ion batteries. They work well enough for now, but they're far from perfect. Liquid electrolytes can catch fire, energy density hits a ceiling, and over time, the battery's performance fades. Solid-state batteries promise to tackle all of these problems, and then some. By replacing the flammable liquid electrolyte with a solid material, these batteries could be safer, longer lasting, and pack more energy into the same size. But that's just a start. This next generation of batteries opens doors to innovations that were previously science fiction. Cars that drive further on a single charge, electric planes that might actually take off, and even medical devices that in or on someone's body for weeks without needing charging. In this episode, we're going to explore what solid-state batteries are, how they work, and why they could be a game changer. We'll start with the science behind the technology, breaking down what makes a solid electrolyte so special, and how engineers are overcoming the challenges of ion movement and material interfaces. Then, we'll look at the current state of development, highlighting companies racing to bring these batteries to market and the innovations that are already happening in labs. From there, we'll consider the potential impact on industries like transportation, energy storage, and consumer electronics, and touch on the limitations and hurdles that researchers still face. By the end of this episode, you'll not only understand the chemistry and the engineering behind solid-state batteries, but also why the technology world is buzzing with excitement about them. Whether you're a tech enthusiast, curious listener, or someone who just wants longer-lasting devices, this episode will give you a front row seat to the future of energy storage. To understand why solid-state batteries are generating so much excitement, we first need to unpack the science behind them. Traditional lithium-ion batteries, the kind in your phone or electric car, rely on a solid or a liquid electrolyte, a chemical medium that shuttles lithium ions between electrodes. First electrode is the cathode, where the ions go during use, or decharging. Secondly, the anode, where the ions go when something is being charged or when it is fully charged. While this works well enough for now, the liquid electrolyte has inherent drawbacks. It can degrade over time, it can leak, or it could even catch fire under stress, and it limits the density of energy that can be packed into the battery. Solid-state batteries replace that liquid with a solid electrolyte, fundamentally changing the rules of energy storage. At the heart of a solid-state battery is that solid electrolyte, a crystalline or glass-like solid that allows lithium ions to move from the anode to the cathode and back again. Unlike liquids, solid electrolytes are non-flammable, making them inherently safer. But the challenge is that ions move more slowly through a solid than through a liquid. Engineers and materials scientists have spent years developing materials, like sulfur-based, oxygen-based, and polymer-based electrolytes, that maximize ion conductivity, or the speed between the cathode and the anode, while remaining stable under high voltage and temperature fluctuations. Each type comes with trade-offs. Those that are based on sulfur offer high conductivity, but can be made chemically reactive. Oxygen-based alternatives are very stable, but they're brittle, which means they're hard to manufacture and hard to use. Finally, polymers are flexible and very usable, but they conduct ions more slowly, limiting their performance. Researchers are constantly experimenting with hybrid designs that combine the strengths of each of these materials while minimizing their weaknesses. Another crucial aspect is the interfaces between the solid electrolyte and the battery's electrodes, again, the cathode and the anode. In a liquid-based battery, the liquid electrolyte naturally wets the surfaces of the anode and the cathode, ensuring good contact and smooth ion flow. In a solid-state battery, achieving that same intimate contact is very challenging. Tiny gaps or imperfections at the interface can dramatically reduce performance, cause lithium dendrites to form, or even trigger failure. Additionally, if the fit between electrodes and electrolyte is at all disturbed, issues might occur. Scientists are exploring methods like coating electrodes with nanoscale layers, using soft polymer interlayers, or applying pressure during assembly to create a perfect fit. These innovations are critical because even if the electrolyte itself is excellent, poor interfaces can negate all the advantages. The anode is also a key player in this technology. Many solid-state batteries aim to use a lithium metal anode, which can store far more energy than the graphite anodes in most batteries that you're likely to interact with on the regular. Lithium metal is lightweight and energy dense, theoretically allowing batteries to store up to twice as much energy in the same volume. However, lithium metal is notoriously tricky. As ions move in and out, they can form needle-like structures called dendrites that pierce the electrolyte and cause short circuits. Controlling dendrite growth is one of the central challenges for researchers. Strategies include optimizing current density, engineering the surface of the lithium metal, or designing electrolytes that are mechanically strong enough to block dendrites without impeding ion flow. Temperature behavior is another fascinating area. Solid electrolytes are generally more stable at higher temperatures than liquid electrolytes, which can boil or decompose. This makes solid-state batteries promising for high-performance applications, like electric aircraft, heavy-duty vehicles, or any other applications where conventional lithium-ion batteries struggle to maintain safety and efficiency. At low temperatures, however, solid-state ion conductivity often drops, which can reduce performance and therefore reduce the benefits of their applications at these low temperatures. Researchers are testing additives, composite materials, and advanced manufacturing techniques to extend the operating temperature range, making solid-state batteries more viable in extremely cold climates. The science doesn't even stop at materials. It extends into the design and the architecture of the battery itself. Since solid-state batteries are completely different from normal lithium-ion ones, scientists are forced to come up with new technologies, one of which is layering electrodes and electrolytes in thin, uniform sheets to improve efficiency and energy density. While another is 3D architecture. Making tiny micro-scaffolds in the battery can increase surface area and reduce ion travel distances. These design innovations allow batteries to charge faster, last longer, and store more energy without increasing weight or size. Scientists are also exploring anode-free designs, where lithium is deposited directly onto a current collector that basically replaces the anode. This makes charging more material efficient and cheaper to build. Manufacturing challenges also play a role. Solid-state batteries require precise control of temperature, pressure, and humidity during production. Any contamination or imperfection can dramatically reduce performance or create safety risks. Techniques like thin film deposition, cold sintering, and roll-to-roll processing are being adapted to make large-scale production feasible. Companies like QuantumScape, Solid Power, and Toyota are pioneering these approaches, balancing the precision required by cutting-edge science with the scalability needed for real-world applications. In summary, the science of solid-state batteries is a delicate balancing act between conductivity, stability, mechanical strength, and interface perfection. It's a field where chemistry, physics, material science, and engineering intersect in exciting ways. Every advance in material design, interface engineering, and battery architecture brings us closer to batteries that are safer, denser, and more durable than anything available today. By understanding these fundamentals, we can appreciate why solid-state batteries are more than just the next step. They're a potential leap forward in energy storage technology, capable of transforming everything from personal devices to global transportation systems. In terms of real-world impact, solid-state batteries are working in the real world. In fact, several companies are racing to move from lab prototypes to real products, each tackling the chemistry in slightly different ways. Toyota, one of the earliest champions, has been running small pilot lines and publicly demonstrated a prototype electric vehicle said to deliver over 700 kilometers, roughly 435 miles, of range within 10 minutes of fast charging. Toyota executives described their 2025 to 2026 goal as limited fleet introduction, focusing on hybrids first to validate durability. QuantumScape, a U.S. startup backed by Volkswagen, reports single-layer cells that have about 1.5 times the energy density of most lithium-ion cells today. Additionally, their multi-layer prototypes have been able to maintain the energy density despite hundreds of charging and discharging cycles. These successes have prompted them to start installing mass manufacturing equipment in California and Germany, hopefully preparing for this technology to be spread. Solid Power, a business built out of the University of Colorado, uses a sulfide-based electrolyte that performs well at automotive current levels. BMW and Ford are strategic investors in the company, and Solid Power recently began shipping prototype cells to both automakers and other places for in-vehicle testing. Another company based in Taiwan has shipped over 7,000 solid-state sample cells to partners and is constructing a plant aimed at mass EV production with these solid-state batteries as soon as the end of the decade. They highlight ceramic-based electrolytes with good low-temperature behavior. Factorial Energy, another contender, uses a unique semi-solid approach. A thin layer improves contact, while most of the electrolyte remains solid. This hybrid strategy aims for easier scaling while keeping the safety benefits. Looking ahead, the promise of solid-state batteries isn't just in solving the limitations of today's technology. It's in enabling entirely new applications that were previously out of reach. One of the most immediately visible areas is the continued development of electric vehicles. Because of solid-state batteries can pack more energy into the same size while being lighter and safer, they could drastically extend driving range without increasing battery weight or driving efficiency. Faster charging is another potential game changer. Imagine being able to charge an electric car in the time it currently takes to stop for a coffee. That combination of range and speed could accelerate the adoption of EVs, making long-distance travel feasible and daily charging far less of a hassle. Beyond personal cars, buses, trucks, and even delivery vehicles could benefit from lighter, denser batteries that reduce energy costs and improve logistics efficiency. Another side benefit to the increased adoption of EVs would be the decrease in greenhouse gases. If we stopped driving all gas cars and vehicles, we would be able to get rid of 15% of our yearly greenhouse gases in the atmosphere. Consumer electronics also stand to gain from solid-state batteries. Phones, laptops, and wearable devices could last days or even weeks on one single charge. Devices that previously needed frequent battery replacements could see lifespans extended significantly. Additionally, solid-state technology opens the door to flexible, ultra-thin, or curved batteries could be integrated into innovative designs. Think rollable screens, smart clothing, or medical sensors that adhere comfortably for the skin for continuous monitoring. In other words, batteries could move beyond being passive components to actively shaping how devices look and how they function. Grid storage represents another exciting frontier. Renewable energy sources like solar and wind generate electricity intermittently. Solid-state batteries could provide safe, high-capacity storage solutions that stabilize the grid, store excess energy, and release it when needed. Unlike conventional lithium-ion batteries, which degrade faster under frequent cycling, solid-state systems could last longer and operate more reliably at high capacities. Smart grid technologies could pair with these batteries to balance demand and supply in real time, paving the way for more resilient, renewable-powered infrastructure. High-demand and specialized applications also benefit. Aerospace, drones, and robotics often face strict limits on weight, volume, and energy density. Solid-state batteries' ability to store more energy without increasing mass could enable electric aircraft with longer ranges, drones that fly farther and longer, and autonomous robots with enhanced operational time. Beyond conventional aerospace, emerging concepts like electric vehicle takeoff and landing, eVTOL, urban air taxis, or other things rely on heavily compact, energy-dense batteries. Solid-state chemistry could be the key to making these futuristic vehicles practical and safe. Speculative applications stretch even further. Public transportation systems could employ rapid charging solid-state batteries for buses or trains, reducing the need for large charging infrastructure and downtime. Energy-dense emergency power packs could provide reliable electricity during disasters or off-grid operations. Even in the realm of robotics, high-capacity solid-state batteries could support machines that work autonomously for extended periods in hazardous environments, from deep-sea exploration to space missions. What ties all these possibilities together is the combination of energy density, safety, and longevity. Solid-state batteries don't just improve existing technologies, They expand what's possible. They could redefine mobility, reshape consumer electronics, enhance the stability of energy grids, and open entirely new fields for exploration and innovation. While many of these applications remain in early stages, companies and research teams worldwide are actively pursuing prototypes and pilot programs, signaling that the next decade could bring more transformative breakthroughs than ever before in energy storage. While solid-state batteries are brimming with potential, translating lab breakthroughs into commercial products is far from simple. One of the most significant hurdles is manufacturing at scale. Producing solid electrolytes with the precise thickness, uniformity, and purity required is technically demanding. Even tiny defects, like microscopic cracks, air bubbles, or contamination, can reduce performance or cause catastrophic failure. Techniques like thin film deposition and cold sintering are promising, but scaling them to produce millions of batteries for cars, phones, or grid storage remains a formidable challenge. Maintaining tight quality control while keeping costs competitive is essential if solid-state batteries are to move from niche prototypes to mainstream use. Another critical limitation lies in stability and durability. Solid electrolytes are generally more robust than liquids, but they can still crack under mechanical stress or expand and contract with temperature changes. These cracks create pathways for dendrites, needle-like lithium structures that can pierce the electrolyte and short the battery. Researchers are exploring mechanically resilient electrolytes and protective coatings to suppress dendrite growth, but no universal solution has emerged. Temperature sensitivity also poses a challenge. Again, solid-state electrolytes conduct ions efficiently only within the limited temperature range. Maintaining performance in extremely cold or hot environments requires careful material selection, careful battery design, and further design of these batteries. Trade-offs between performance and safety are another key consideration. Lithium metal anodes offer enormous energy density, but the risk of dendrites means engineers must balance aggressive energy storage with safe operation. Similarly, faster charging can stress materials and increase heat, potentially shortening lifespan or compromising safety. Finding the sweet spot between energy density, charging speed, cycle life, and safety is a central focus of our ongoing research. Finally, timeline uncertainty tempers enthusiasm. While companies like QuantumScape, Solid Power, and Toyota are making impressive strides, widespread consumer adoption is unlikely to happen overnight. Current projections suggest that high-volume deployment for electric vehicles may still be 5 to 10 years away, with consumer electronics and grid applications lagging even farther behind. Researchers and engineers must not only perfect materials and designs, but also develop cost-effective, high-throughput manufacturing processes before these batteries can enter everyday life. In short, the challenges facing solid-state batteries are as real as their promise. Manufacturing precision, stability under stress, balancing performance with safety, and scaling up production are hurdles that must be overcome. Yet, these technical limitations are actively being addressed in laboratories and pilot plants worldwide, setting the stage for a future in which solid-state batteries finally deliver on their transformative potential. Solid-state batteries represent a major leap forward in energy storage, offering a glimpse into the future where our devices, vehicles, and infrastructure are safer, longer-lasting, and more efficient. By replacing flammable liquid electrolytes with solid materials, engineers are unlocking higher efficiency densities, faster charging, and greater durability. Beyond performance improvements, these batteries open doors to innovations that were previously science fiction. Electric planes that could take flight, wearable devices that run for weeks without charging, and grids capable of storing renewable energy more efficiently than ever before. Yet, the journey from laboratory to mainstream use is ongoing. Manufacturing precision, material stability, dendrite control, and scaling up production all require careful engineering and innovative problem solving. Even as these challenges are addressed, solid-state batteries promise to reshape the way we think about energy, giving us tools to decarbonize transportation, enhance consumer electronics, and support global energy systems in more sustainable ways. As we look ahead, the excitement around solid-state batteries is more than just chemistry and engineering. It's about potential. These batteries could redefine mobility, communication, and energy storage within just a decade. The energy revolution isn't just coming. It's being built in labs today, and solid-state batteries are at its core. By understanding their science applications and limitations, we gain insight into a technology that could power the future safely, efficiently, and sustainably.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.